Ritesh, is the screen visible? I'm sharing right now.
No.
Okay, let me
Okay.
again reconnect it. Okay,
Yes,
now.
visible.
Okay, thanks. Okay, good evening, everybody. And the topic that I will discuss today is geometry and line elements, the concepts that were introduced by James B. Hartle and Bernard F. Schutz, the famous scientist who developed lots of the contents on this topic, and they used it as a basis of general relativity and many other branches of physics as well as mathematics. So let's start with this, and I will start with the very basic concepts of geometry that is known, or few may not know it, but that is interesting. So let's start. So our whole purpose of this is gravity is geometry, and we have to see how geometry is linked up to the gravitational forces and other things, other branches of mathematics. Okay, so this experiment, I start with the conclusion of those experiment that was conducted in 1820s. C.F. Gauss, you all know Gauss, a famous mathematician, scientist. What he did, he tried to verify the standard theorems of Euclidean geometry of space. That is, sum of the interior angles of a triangle is 180 degree. Now that was a very nice approach, and but what he did was very strange. He went to the top of a mountain, and then he took three mountain tops as vertices of a triangle. He used light rays to connect those tops, and somehow calculating this way, that way, that was a lot of tough calculation that he did at that time. As people see, he did it, and he deduced the result as 180. Yes, it is verified. The sum of the angles of a triangle was 180 degree. Okay, so he was happy, he concluded this. But if I look at that scenario in the present sense, means what he calculated, the formula that will actually fit to that calculation, it is written here. Sum of the interior angles of a triangle in radians minus pi, it will be area of the triangle upon r plus. Now these notations, r plus and m with plus, these are the mass and the radius of the earth, the planet on which we are living. So the main formula that should hold, actually it is this formula, but somehow Gauss calculated it and he showed it is 180 degrees. But after many years, when this formula was derived at, and again those results were verified, it was found that Gauss was not exactly right. There was an error, but that error was so small, so minute and insignificant that to some extent we can accept his. Okay, but the concept that was missing in his calculation was he used the mountain peaks and he used large distances, and at large distances the geometry is not flat, geometry gets distorted, it is curved, and the curvature has to come in. So in this formula that is present on the screen that you all are able to view, g into m plus upon r plus c square, this term that is added to this formula, actually this contributes to the curvature effects that is produced by m is the mass of the earth and r plus is the radius of the earth. So that was an interesting case where our famous scientists and the past peoples had so much enthusiasm in verifying all the mathematical results. And let's move on now. So now I will try to focus more on geometries, how different geometries are defined, and what were Euclidean geometry, what are the theorems, and where do they pass and fail in our present context, and what we need to do. So first of all, Euclidean geometry of the plane. Now this again a very simple result. You all know sum of the interior angles of a triangle is 180 degrees. We all know this, so it's acceptable result. Another relates the ratio of circumference of the radius of a circle to the radius of the circle. You all know it's a very basic level, 6th, 7th, 8th level mathematics. There's circumference upon radius, it is 2 pi. A well-known result, all of you know this. But let's see what will be the changes if I change the geometry on which we are measuring these things. For example, if I move from flat to curved surface, what will be the changes? And then we'll move on to some general results on this. So let's look at that same result on the surface of the sphere, and let's see what will be the changes. So surface of the sphere, it is a different two-dimensional geometry. Why it is different? Because Euclidean it is flat plane, well and good, but in sphere it is not flat. So for the spherical triangle on the surface of the sphere, if I create a triangle and then I measure the sum of the interior angles, it will not be pi, it will be a upon capital A upon a square. Where is capital A? It is the area of the triangle we are talking on the surface of the sphere, and the small a is the radius of the sphere. So this formula is actually interesting, and it's a very simple formula, because if A, that is the radius of the sphere, if I go on increasing it, I fix A, that is the capital A, that is the area of the triangle that I have taken. If I go on increasing the radius of the sphere, we'll find that this term becomes insignificant, A upon capital A upon A square. And ultimately, the sum of the interior angles will reduce to pi, that you all know. And that is a well-known result. So this term, that insignificant term, it plays a role when A is small. And then sum of interior angles will not be 180 degrees. So another change that we see, and it is only due to the change in the geometry, because now we are talking about two-dimensional geometry. Now further, in the sphere case, if I take the circumference upon radius, circumference to the radius ratio, it is 2 pi sine r by a upon r by a. Again, a is the radius of the sphere, and in this case also, if r is much less than a, then the right hand side reduces to the flat space result. So these anomalies that you all know, that you are seeing, it arises only because of the geometry. So geometry has a lot more than the simple things. So let's move on now. So the natural question is how we are doing these things. Often we notice it, often we not notice it, but visualizing a three-dimensional curved geometries. Okay. And how do we visualize it? We visualize it in viewing in a higher dimension. For example, two-dimensional sphere, we visualize it in Euclidean three-dimensional space. So that is so good. But what about if I have a three-dimensional object? How can I visualize it? For that, I have to move it to a four-dimensional. But four-dimensional is impractical in visualization. By mathematical calculation, okay, I can do this, that, and get some view of the picture. But exactly what will be the picture, it becomes really difficult. So let's move on to something simple way of getting the essence of geometry. So we will not talk about intrinsic geometry, intrinsic description of geometry, something that depends only on the surface on which we are talking and not on the space in which it is embedded. That is important. For example, if I am on the surface of the sphere, I should only look on the surface of the sphere in describing its intrinsic geometry. I keep an ant on the surface of the sphere, on the surface of the potato, then he should just moving on the surface deduce all the properties of that surface without moving to extra higher dimension. So let's see how this can be done. So for flat plane, you all know there is Euclid's 5 axiom, you know it, and we apply it. For example, 2 points determine a unique line, parallel lines never intersect, all those properties. But here we'll see how we can deduce those results. Okay. So what is important that we'll now move on is to describe a geometry. What we'll do, we'll take the distance between 2 points. Any 2 points, we take a distance, infinitesimal distance, and that distance will play a key role in describing the geometry. Okay, so for distance between nearby points, using that we can find the distance along a curve. It can be built up by integration. Straight lines, these are curves of shortest distance between 2 points. Angles are ratios of length of arcs to their radii when those radii are small. So all the mathematical things that we can calculate it in terms of the elementary small distance between two separated points. So now we'll see how we can use those concepts. So let's move on and let's talk about Euclidean geometry of the plane, the concept that you all are aware of. And so here on the left hand side, I have a figure. And in this figure, I have 2 points. It's a very elementary mathematics. I have taken 2 points, x, y, with the coordinate xy. One is point this, another point is with the coordinate x plus dx and y plus dy. On the right hand side, again, the 2 points, but I have taken polar coordinates. Okay. Now, coordinate system, you all know, is just a label. It's just a label to refer to a system. Okay. You cannot assign any importance to it because I can change the coordinate system. But the geometry of a surface which we are talking about at any instant, that geometry is independent of the coordinate system we use. For example, a sphere will remain a sphere if I use Cartesian coordinate, if I use polar coordinate, if I use any other absurd coordinate system you have built on that surface. So on the left hand figure, in Cartesian coordinates xy, the distance ds between the points xy and x plus ds, y plus dy, you all know Pythagoras theorem. It's a very simple result. Ds square is dx square plus dy square square root. It's a very simple result, a well-known result. Now, using the simple distance concept that is written on this screen, we can verify all the Euclid result. We can verify, in fact, the two results that I saw, that you all saw on the previous slide. That is the circumference upon radius ratio for a sphere and other things. So we'll calculate it and then we move on to the more general concept. So if I write the same distance between 2 points in terms of polar coordinates, for example, if the 2 points have labels as r phi and r plus dr and phi plus d phi, then the distance between the 2 points ds square is dr square plus r d phi whole square square. It's a very simple concept. You all must be knowing. We can change the coordinate system. We can write the distance between 2 points like this. Okay. Now using this simple concept of distance between 2 points, we will try to find the result that we just now saw, that is the circumference c in case of a circle in the sphere. So let's, for example, calculate the ratio of the circumference to the diameter of a circle of radius r. So first of all, look for it. So x square plus y square, this is the equation of a circle that you all know in a 2 dimension. And we will try to calculate the circumference. So circumference c, it is integral of ds. So we'll try to calculate the circumference by elementary mathematics using the distance between 2 points, ds. Okay, and ds is what? Dx square plus dy square square root. So it's a very simple calculation now, and we use simple mathematics 2 times, and dy by dx, we take dx common, and dy by dx is can be calculated from x square plus y square is equal to r. So that is done, and then on changing the variable, we get the circumference c is 2 pi r. Now, the purpose of showing this calculation was just to link up the geometry with something that is distance between 2 points. You all know distance between 2 points, so this result, circumference is 2 pi r, it is evaluated just by using the concept of distance between two infinitesimally separated points. So now we'll generalize this concept. Okay, so similarly for so geometry specified by line element, that is what I wanted to say. And the line element is written in a quadratic relation, ds square is dx square plus dy square. The importance of this relation is that if I'm on the surface, on a 2-dimensional surface, for example, I'm just using the 2 coordinates x and y, no other coordinates. And I'm calculating this distance. And using this infinitesimal distance, I can verify all the theorems, all the axioms that is fundamental in these mathematics courses. So this result, ds square dx square plus dy square, that is the line element, is important, and we'll use it a lot and we'll develop it. So similarly, for the non-Euclidean geometry of a sphere, I started with the sphere. I did some mathematical calculation on the surface of the sphere, some axioms we proved on the surface of the sphere. Okay, so again, for all those axioms that I calculated, you can verify those by just using this distance function on the surface of the sphere. Again, ds square is a square d theta square plus sine square theta d phi square. A is the radius of the sphere. And again, using this small distance between 2 points on the surface of the sphere, using the ds square, I can calculate this ratio circumference upon radius for the surface of the sphere for drawing any circle on the surface of the sphere. I can verify any other mathematical result using this distance. Just we have to integrate that distance, move along the curve, follow all the restrictions that is valid for that curve, and we can prove those results. So the geometry is specified by line element, that's clear now, and that line element needs to be developed and focused more on. So consider, and as an example, the line element ds square a square d theta square plus f square theta d phi square. This is the line element on, and it is for a 2-dimensional coordinate system which we are taking in theta and phi terms. So ds square is a square d theta square f square theta d phi square. Now to show you the essence of this function f square theta that is appearing, if I substitute f theta as sine theta here, so ds square is a square d theta square plus f square theta, that is sine square theta d phi square. And just now we saw in the previous slide, if you have observed it, that it is the surface of the sphere. So this line element, on substituting f theta sine theta, we are obtaining the surface of the sphere. Very good. Now if I change this f theta, if I change this function to this function sine theta into 1 minus 3 by 4 sine square theta, and again I substituted here ds square, and then you all have softwares, you can substitute this line element, you can integrate it, and it will be a peanut geometry. So you look, the moment I change this ds square, the moment I change the coefficients of this ds square, for example, a square appearing as a coefficient of d theta square, a square f square theta appearing as coefficient of d phi square. The moment I change f theta, the whole geometry changes. So this line element that I'm talking about, it is the essence of every geometry. It is giving you the real thing, what you are thinking of a geometry. It is a flat space, it is a curved space, it is some weird space, it is a peanut geometry, it is something like this. All depends upon this line element. And further, very important, all depends on the coefficient of this line element. For example, if I make these coefficients change, the geometry will change. So let's move on now. So now I will like to talk few things related to be discussed when we move from one coordinate system to another coordinate system. For example, you are sitting there and I may be in a motion, and we both are observing any object, any experiment. So there is a relation between your observation and my observation. And how to relate those two observations? For that, we need coordinate system and a transformation between the two coordinate system. So that is done here. And before that, I need to address one important thing, that is inertial frame. What is inertial frame? That is important. So supposing I have three particles that is moving randomly, three particles. So and I have been asked here to construct an inertial reference frame. So what I'll do, I'll pick up a particle, choose it as the origin of the coordinate system. I will insert three perpendicular Cartesian coordinate system on it, x, y, z axis. And for the further observation of my experiment, I will allow the particles to move parallel, allow the axis to be parallel, and they should not rotate throughout the motion. And then with respect to that particle, respect to that coordinate system, respect to that origin, I can observe all the other motion of the particles. And the coordinate system that we construct in such cases, it is inertial reference system. It is an inertial frame. So I'm talking about all the results from now onwards on inertial reference frame. I talked about the inertial reference frame. So let's see what will be the displacement and rotation and uniform motion between two observers. For example, I may be one observer, you or anyone may be another observer. One may be in motion, one may be in rotation, one may be in uniform velocity. So how are the coordinate system related? So if one of the observer has coordinate system as x, y, and z, another observer has coordinate system as x dash, y dash, and z dash. So if the two observers are just displaced, means they are stationary, they are displaced, and they are looking at an experiment, then this is a very simple result, that x dash is x minus t, that is the x coordinate measured by one observer. Similarly, the y coordinate is y, z coordinate is z, because we have displacement only along the x-axis. Similarly, let's talk about rotation. Rotation by an angle phi. If the two coordinate system are related by rotation by an angle phi, then in one coordinate system x dash, y dash, z dash, or x prime, y prime, z prime, it is related to the original coordinate system x, y, z by this form. So x prime is cos phi x plus sin phi y, y prime is minus sin phi x plus cos phi y, z prime is z. And similarly, if you have uniform motion by velocity v along the x-axis, two objects, they are moving, they have a velocity, and they are observing any experiment, any event, then x prime will be x minus vt, y prime will be y, z prime will be z. Now these are very simple results actually, and you can find the derivation in any of the elementary level books on maths or on physics. But we are trying by this to relate the two observations, or more focus is on observing any two experiments. So let's move on to something that you must have heard in your life some way or from some sources, principle of relativity, what it is, how it is important, and how mathematically these things are framed. So principle of relativity, it's an interesting concept, and it was given by many scientists until it was highlighted by Einstein. He also used it as an equivalence principle. So let's talk about principle of relativity. What does it say? Identical experiments carried out in different inertial frame give identical results. Or in other words, if we have two coordinate system, inertial reference frame means coordinate system. If we have two coordinate system, and in one coordinate system there may be some experimenter, he does some experiment and he is happy that his results are well and good, and he asks me to confirm it, and I also do the same experiment, do all those, set up all those apparatus, and I do the experiment, I also find the same result. That is, the experiments are identical, their end result will also be identical. So identical experiment carried out in different initial frames, they give identical results. It appears to be simple, but it is a very important result. It has foundation of general relativity, theory of relativity that Einstein gave, and all the other mathematical things that we'll see now. So another thing is space-time. This is also very, very important concept. What is a space-time? Till now, we talked about space as a separate entity. We talk about the time as a separate entity. If I have any point P in the space, for example, I am sitting here and I am giving a lecture, but I am sitting at a fixed coordinate system XYZ is constant, but time is not constant. Time is in motion. So in one way, for example, if Newtonian follower observe me, they will say that I am stationary, I am sitting. But if someone who had read Einstein, he observed me, he will say, no, you are not stationary, you are in motion. You are in motion because time coordinate is continuously changing. Time is changing. So you are in motion. So ultimately, by a lot of other mathematicians and physicists, it was thought that these two are not separate entities. It was Minkowski who said, no, we should just use them together and txyz. So it was combined together and we talked about the four-dimensional txyz. So this four-dimensional component, four-dimensional system that we talk about, that will be called space-time, because space and time are merged together. Okay, so initial reference frames we are talking about, and we are talking about initial reference frame in space-time concept, where we have a time component also, where we have x, y, z, that is the space components also. And another observer who is another inertial reference frame, then he will use a different set of coordinates as t dash, x dash, y dash, and z dash. So from now onwards, if I need to draw any experiment and the reference system, I will use two components, in fact four components, but on space I can only show two components perfectly. So I will use the x coordinate and I'll use the t coordinate. T coordinate will be the time, x coordinate will be the space dimension. And any event will be represented by the time at which it occurred and the space component at which it occurred. And further, as I said just now, stationary, the things that are stationary in space, actually they are moving with time. So that has also to be kept in mind. And all those concepts of word line, other things, they originate from here only. Okay. So now we started with geometry, and I was discussing on geometry only. So what is the geometry of this flat space-time? Because I started with 2-dimension, I moved on to 3-dimension, I talked about sphere, I talked about the pinit geometry. So the natural question arises, okay, now you are talking about the 4 dimensions, t, x, y, z. So what is the question is, what is the geometry? What is the intrinsic geometry of the 4-dimensional space-time, flat space-time? And further, we need the geometry in terms of the distance between two infinitesimally separated points. So that distance between two infinitesimally separated points, ds square, it is given square minus c, it is given as minus c dt square plus dx square plus dy square plus dz square. Now this derivation, if you ask, it has a lot of experimental setup for this derivation, but you can verify it, you can go for books to search it out. This is given in this form. This is the distance between two infinitesimally separated points in the space-time, not in space, in space-time. So one may ask, okay, in space we had distance between 2 points given by a Pythagorean result or from depending upon the geometry. But in space-time it is different, because here we have a minus sign in front of time component or time coordinate dt, and then we have plus sign in terms of ds square, dy square, dz square. So in our non-space-time mathematics that you all know, there the distance was always positive and we were happy with that. But here it is not so. Here if you observe as the distance, it can have positive, negative, as well as it can have zero, because of this simple negative sign that is appearing here. For example, if ds square plus dy square plus dz square, they are equal to c dt square, the distance between two events, even though they are separated, in space-time, the distance will be zero. Okay. And further, if dx square plus dy square plus dz square is positive, it is more than c dt square, the distance will be positive. If it is less than c dt square, the distance will be negative. So here we are obtaining three kinds of distances. So ultimately, it is not the same geometry that we have seen in Cartesian coordinates in Euclidean geometry, and so on. So this geometry is interesting, and let's see what this geometry tells us. So if we have this the delta x square or ds square, it is positive between 2 points in space-time, we call it space-like separated points. If it is zero, it is null separated. If it is negative, it is time-like separated. So these separations are in terms of events. So the interesting thing is, if I take ds square is equal to 0, then I have c dt square is dx square plus dy square plus dz square. And dx square plus dy square plus dz square upon dt square, that will be c square. Here c is the speed of light. So what it says is, if two points are null separated, we call it as null separated. If two points are null separated, means they are connected by a light ray, because the distance upon time, it is equal to speed, and the speed is the speed of light, here c. Means two points are connected by light ray moving from one point to another point. And if it is negative, means dx square plus dy square plus dz square, this is less than c dt square. In that case, what it says geometrically, it says that, okay, if we have two events for which delta square is negative, then they can be connected by a light ray. Okay, and if it is positive, means space-like separated, means this is space-like separation ds square dy square dz square, it is more than c dt square, and such experiments are very difficult to observe. Okay, so this was just an introduction of light cone, and there's a figure also at any point in space-time. At a point P, you can draw this, you have light cones, and the interesting part about this light cone is whatever is inside this light cone, in the upside or in the bottom side of this figure, they can be connected from this point P. They are events which can occur from P to in moving to that event. Whatever is outside that light cone, they're immaterial, they don't affect P, and P is not affected by them. And along the diagonal, along this dashed line that is appearing here, it is the path of a light ray in this space-time diagram. See, the vertical axis, the time axis, and the horizontal plane, they are represented by x, y, and z coordinate system. So this is a light cone, and in any experiment we can draw a light cone, and the physical objects like us, like in our planet or whatever we observe here, all those objects, they follow the light cone, they follow the path inside the light cone. That is inside this cone from the back, that is from the past, they are appearing to the present, they will be inside this cone. And if their speed increases, they will follow along these, the end, or that is the generator, they will follow these axes, that is along the ray, along the path in which light they can move. Otherwise, if the speed is less than light, speed of light, they will be inside this light cone. So this is the geometry given by this is in geometry of flat space-time. And using this geometry also, I can study a lot about this flat space-time, as we have studied about sphere, as we study about our plane, as we study about peanut geometry. You use this geometry, you use this line element, and you can explore lots of things about the flat space-time geometry. So now let's move on to the thing, another thing that we talked about, two coordinate systems. And if we have two coordinate systems that are inertial, that are space, we are talking about space-time, and we have two space-time coordinate systems which are inertial. Then from one coordinate system to another coordinate system, we have a connection. We can, if an observer observes some experiment, the another observer wants to see the result, he can use the components from the first observer, and he can calculate the results on his coordinate system. And such transformation is called Lorentz transformation or Lorentz boost. So this is connected by the simple result t dash, and that is in the new coordinate system, new inertial frame. It is this gamma times t minus vx upon c square. Theory x dash is gamma times x minus vt. Y dash is y, z dash is z. So here we have introduced gamma as 1 minus v square upon c square square root, where v is the velocity of one observer with respect to another observer. So there are two observers, there are two inertial reference systems, and the relation between the observations of those two observers, it is given by this simple mathematical formula. Okay. So now I'll talk about equivalence principle and what is equivalent to what. After talking so much about the geometry that is the base of all those things, let's see what is equivalence principle. So experiments in sufficiently small freely falling laboratory over sufficiently short time gives results that are indistinguishable from those of the same experiment in an inertial frame in an empty space. Okay, now let me give you an example that started all this. So once the famous man, the Mr. Special Relativity, that is Einstein himself, he was standing on the top of on a floor, and he just imagined if a floor from beneath vanishes, what will happen to all of us? And he calls this as the happiest thought of his life because it changed many things and it made him to visualize those concepts and the changes that are till date experimentally verified. And lots of things are being developed till now on those mathematical results. So the result is, supposing you fall on the gravitational field, supposing you fall from the top of a tower, you took a jump. Of course, don't take such jumps, but just assumption. If you take a jump from the top of the tower and you will be falling with an acceleration that all knows, that everybody knows. And the important thing is that if I don't tell you you are in a free fall, this is called a free fall. If you are in a free fall and don't tell you, I keep you inside a box and I make you fall. You don't observe anything. And if the fall is for a sufficient period of time, then during that time, it is very difficult to say whether you are in a gravitational field or where you are in an outer space far from any gravitating object. This is a practical experiment, it's true, that you cannot tell the difference. You may have some experimental setup, then only you can say that I am in a gravitational fall, but that also for sufficiently long experiment to be conducted. For a short moment of time, for a small moment of time, it's very difficult, you cannot distinguish. So falling in the gravitational field, it is often said it is undetectable. That is true here. So that was equivalence principle, that you fall in the gravitational field for a small moment of time, for a very short time, it's very difficult to distinguish between that whether you are in gravitational field or whether you are in outer space far from any gravitating objects. So that's what equivalence principle says. And now I was talking about space-time, I was talking about geometry, one more geometry to you. Now this line element that is present, again I have talked about line element, this is a line element. Now this line element, ds square, it is minus 1 plus 2 times phi upon c square c dt whole square plus 1 minus 2 phi upon c square dx square dy square dz square. I showed many line elements to you. This is also a line element, but the important thing here is, okay, the structure is same. The component of dt, again it is negative. The coefficient of dt is, again it is negative. The coefficient of dx square, dy square, dz square, it is positive. Further, as in p-net geometry, I asked you to observe that f theta function, when it changes, it has different geometries. So here the coefficients, if you observe, of c dt square, it is 1 plus 2 phi by c square. And similarly for dx square, dy square, dz square, it's not constant, it is some function. Where this phi function, actually, it is the gravitational potential, potential due to mass that is creating the gravitational field. And this line element, this is the line element which we use. This is for slow moving creatures like us, all the planets adjacent that we observe, for all the living beings on the earth that we observe, and for fast moving truck or the fast moving truck that you may take, they all follow this line element. So this line element, ds square minus 1 plus 2 phi and so on, this is the line element that describes the Newtonian geometry. And if you observe it, now we are talking geometry, we are not talking any force, we are not talking anything else, we are talking everything in terms of geometry, because it is the geometry that changes. The geometry, if it is flat, it is a flat space-time. If it is curved, we are moving in curved space-time, and this is a much intrinsic character, intrinsic nature to discuss any surface. So this is the geometry in space-time terms, that is Newtonian geometry. Newtonian gravity is described by this line element and this geometry, that is ds square and so on. It is written like this. Okay, so far so good. So now I move to another concept that we call by the name of metric. Okay, so what is a metric? The same line element that I wrote many times that we saw in the previous slides. It is called actually metric, and it is written in this concise form. And this is the beauty of mathematics and the beauty of the summation convention that was invented in 1900s as the starting time, that ds square is g alpha beta dx alpha dx beta. In present day notation, if I have to write it down, I should write summation g alpha beta dx alpha dx beta. But this is actually summation convention, and what is often said is, if we have two indices which are repeated, one with and occurring in pairs, for example, alpha alpha occur in pairs, beta beta occur in pairs, so it is understood it is summation. So we skip the summation sign here and we just write it like this, and believe me, it simplifies a lot of calculation, a lot of lengthy formulas. It's just written in this concise form. So ds square is g alpha beta dx alpha dx beta. The coefficients are the metric g alpha beta. and these are actually tensor quantities, and a lot of tensor calculus and tensor mathematics is involved here, but I don't go into don't those details. So we just keep to limited things that we need to discuss here. So G alpha beta, it is the coefficient of this dx alpha dx beta. So if I need to expand it, in a four-dimensional coordinate system, tx, y, z system, that is in a space-time, so dx0 alpha beta runs from 0, 1, 2, 3. So dx0, that will be dt square. Similarly, dx1, that will be dx square. dx2, that will be dy square, dz square. Similarly, there may be cross terms also. For example, alpha can be 1, beta can be 2, so it can be dx, dy, dt, dx, and so on. So it is actually representing a very large combination of terms, but in concise form it's written like this. In fact, this metric ds square that is written for space for Newtonian gravity, it can also be written like this. Only thing is I need to focus on what are the coefficients. So if I need to calculate the coefficient for this metric, the coefficients are g00, it is this component of dt. Then we have g11, it is this component, g22, that is coefficient of dy square, and g33, it is coefficient of dz square. So overall, we can define geometry of a surface by the line element, where the coefficient, that is the metric, they give us a detailed structure of the surface. But further, I told you about change in coordinate system. So if I change to coordinate system, definitely this g alpha beta, this coefficient will change. But remember, geometry doesn't change. Or you may use any experimental setup, the geometry won't change. Only the line element form will change, geometry won't change. Okay, so now let's talk about local inertial frame and the experiment that I just started with, that if you are on a free fall on the surface of the earth, if you jump from the top of the tower and something like this, then I told you the effects of gravity is eliminated. You don't feel the difference. Mathematically, it amounts to saying that this g dash alpha beta, it is eta alpha beta. Remember, g is the same term, ds square, g alpha beta, dx alpha, dx beta, where g alpha beta, it is the coefficient of these dx and dx terms. So mathematically, what it amounts to say that at any point during your free fall, at any point, the metric, that is this component g alpha beta, it can be reduced to eta alpha beta. And eta alpha beta is what? It is a two-dimensional metric where the diagonal components are -1, 1, 1, and so on, and the remaining off-diagonal terms are 0. So this g dash, the metric, it is actually whatever combination of terms it had, but at any point I can make it constant. I can make it as -1, 1, 1, and this is the metric of the flat space-time. If you remember, I gave you the metric of the flat space-time in Koski metric. That was minus dt square plus dx square plus dy square plus dz square. That geometry was described by flat space-time metric. So this says that at any point g dash, that is this metric coefficient, it can be made to a constant, or in other words, the effects of gravity can be neglected. Physically, it amounts to saying that. Mathematically, it amounts to saying this thing. Okay, so this is one experimental set, and this is one experimentally verified result. And further, in addition to this, that not only g prime is eta alpha beta, or g dash, that is in the coordinate system, I can make it constant. Not only this, but the derivative of the metric can also be made to vanish at a point. That is del g upon del x. This derivative of the metric, it can be made to vanish. So one may ask, okay, this is fine. At a point in a free fall, at a point in a gravitational field, I can make the metric coefficient constant. Well, I can make the derivatives of the first derivative of the metric constant. Okay, then this means that metric is useless in calculation, because if I can change it, if I make it a constant, then how am I visualizing, or how do I measure the geometry of the surface? So that intrinsic geometry, it is hidden not in just the first derivative, it is hidden in the second derivative. And believe me, if there is a curvature that is mathematically verified, if you have a curvature on a surface, on a space-time, then this derivative that I have taken, the second derivative onwards won't be 0. It is non-zero. So whenever there is curvature on a surface, on a four-dimensional space-time surface, then this second derivative won't be 0. And from there, the concepts of Riemann tensor and all the tensor quantities do originate that measures the curvature. And if we have non-zero components, then the curvature isn't zero. So this is what mathematically says that if you are in free fall, so at a point I can make the gravity to vanish. At a point, I can make the metric coefficient as constant, and at a point I can make the first derivative as a constant, as a zero. But the second derivative onwards won't be zero, so they amount to curvature. And all those concepts are involved in tensor calculus. We calculate Riemann tensor, Ricci tensor, Ricci scalar, and they give us a clear picture of the space we are talking about, whether it is curved, whether it is flat, and so on. So that needs a separate discussion on all those issues. Okay, so that's all for today. And any questions you may ask on this?
Okay, thank you, Dr. Shukla, for your nice talk on geometry and line element. Actually, we know that the shape of circle, rectangle, etc., this shape fall under geometry, but their area of each shape fall under algebra. So this is the basic connection between algebra and geometry. So nice to see here. So thank you, Dr. Shukla, for your nice presentation on the geometry and line element. So from the audience, if you want to ask any question.
Sir, hello, sir. Good evening. Sir, good
Yeah,
afternoon, sir.
Yes.
Sir, you said that the rotation about z-axis by an angle phi. So, but z prime was z is equals to z. So, sir, I didn't get that point.
Rotation about z-axis? No, not about z. That was time axis. In the vertical direction, we had time axis. Okay,
Okay.
and we considered rotation among two coordinate system. One was supposing x and t in two dimension. I will represent only in two coordinates. Okay, so one reference system was x and t. Another reference system was x dash and t dash. So x dash t dash, it is rotated with respect to xt by an angle phi. And then we had those transformation that I presented.
Okay.
Okay, it was not for z axis.
Okay, sir. Okay. Thank you, sir.
Okay. Okay.
Okay, thank you, sir. Sir Gupta, sir.
Okay, thanks, Ratnesh, sir.
Thank you very much, sir, for this interesting talk. Participants, we will meet again tomorrow at 10:30 to 11:30. So the tomorrow lecture will be delivered by Dr. Nutan Kumar Tomar from IIT Patna. He will talk about applications of linear algebra in control theory. So thank you everyone. Thank you, sir.